Welcome to Scrap Paper and Philosophy, everyone. I'm going to begin with a thought experiment, and why don't I play back, and I'll ask you a question about this later. Okay, so I'm going to ask you a very simple question. Are you satisfied that what you saw on the screen is what took place in the concert hall? And your answer should be no way. Now, if I ask you, are you satisfied that what you heard is what took place in the concert hall? Your answer should be a resounding yes. In fact, what you heard is so exactly like what took place in the concert hall that a caveman would think it's absolutely indistinguishable from magic. It's absolutely indistinguishable from a time machine into the concert hall. And the point is that the electromagnetic systems that are used to create such audio are not acting as a space machine. They are acting as a time machine. So let's begin by just scratching the surface of information theory. In information theory, we know that there's a trade-off between how fast we can execute a computer task and how much storage space the computer task requires. And if you're a computer programmer, you know exactly what I'm talking about. An example would be that merge sort for sorting an array is faster than bubble sort, but the trade-off is that merge sort requires more space because you have the requirement of a temporary array, which I believe bubble sort doesn't require. But in database theory, I imagine this trade-off just screams at you because there's some kind of optimal point in your database design that you are looking for. So, well, let's go to the luminocentric hypothesis, which I call it the principle, because I'm absolutely convinced it's true, in a very stubborn sense of the word convinced. So there's a trade-off between how fast an electromagnetic wave is spinning and how much space in the sense of the amount of room in a circle that it takes up. And we saw that last time. But we are not, I mean, how can I expect the viewer to be prepared to deal with this concept if I'm not prepared to quantify it right now? So I'm just trying to scratch the surface here. So let's retreat to physics as a warm-up where we know exactly what we're doing. There's a whole history behind the concepts we're going to use. We're going to derive the law of conservation of momentum, and we are going to compare it with the law of conservation of mass and energy. So let's go. And the reason why the law of conservation of momentum is important is because quantum mechanics is absolutely obsessed with it. It's like the one thing that a quantum physicist will hold absolutely for certies to be true, this law of conservation of momentum. Let's look at very closely at the conservation of momentum. Okay? Very, very closely. Let's do a closer than this. So the requirements, and this is a hidden requirement, is that the amount of stuff in the universe can be quantified as a number, m equals something. So Newton is trying to quantify nature, and he's going to require that a number can be associated with the amount of stuff in the universe. It's a very subtle requirement only because it's hidden from view usually. The other requirement is more explicit, which is the amount of stuff, m, can be measured. It equals to the force. And here we assume that we can apply a constant force at least for a certain duration. If you can squeeze out an interval in time where you know this force is constant, then you can measure the mass. Because what you do is you divide the constant known force by the change in the velocity of the mass over the time interval where you were able to hold that instantaneous force constant. Moving on. Wait a second. Did I? Okay. I don't know what's happening here. Maybe if I go like this. Oh, no. Like that. Okay. Mass doesn't change by assumption, it's the amount of stuff there is. And velocity doesn't change because there are no forces in vacuum. So we have a product, mass times velocity, it equals to momentum. We know that neither of the factors is changing. We know that the mass isn't changing by assumption, and we know that the velocity isn't changing because there are no forces in vacuum. And the idea is that the mass is traveling in vacuum. And the conclusions is that, well, if you want, this first expression is what we would learn in a physics class without calculus, and the second expression, dp dt equals 0, is what Newton would have alluded to, and it's what we would learn in a physics class with calculus. And this is a very interesting expression because what we're really getting at is we're using the law of conservation of mass to hold mass constant. If we're going to look at anything that's changing, we're going to look at velocity. And what dp dt is, which is the derivative of momentum with respect to time, is really m times dv dt, the derivative of velocity with respect to time. We assume, okay, that this mass is constant with respect to time. We don't know the law of conservation of mass and energy. We really don't know the law of conservation of mass and energy. We only know the law of conservation of mass. We are assuming that m is constant, and we are using dv dt to say dp dt equals 0. Now we know what dv dt is. dv dt is acceleration. And actually, it's the second derivative of space, right? So instead of v, we want the first derivative of space here. And instead of a, we want the second derivative of space here. And we know what mass times acceleration is, okay? Mass times acceleration is a force. And we are saying the force is 0. That's all this expression is saying. Of course, the law of conservation of mass follows from embodying the universe inside the vacuum. Because as soon as we embody the universe inside a vacuum, we know that the universe is not experiencing a net force. So there. Now, I want to get back to what I was saying earlier about the law of conservation of mass versus the law of conservation of mass and energy. Because what's actually happening with black body radiation, we know, is that electromagnetic stuff is oozing out of masses, even though we don't see it. What we do see is the photonic imprint, so to speak, of the mass. What I mean by photonic is electromagnetic radiation within the band which we call photons, within the visible spectrum. So, other than the visible spectrum, we know that masses are oozing out this black body radiation. And we are going to adjust to the law of conservation of mass, because the mass system is losing this radiation in an energy term, in terms of energy, not in terms of mass. Well, if there was a mass and it left behind the black body radiation, and you see where I'm getting at with this, the mass did not emit, the mass did not send the black body radiation flying out. Or maybe it did, but that's what the physics is saying. It did. It emitted. The black body radiation went flying out of the mass. And well, if we were to take the luminocentric principle seriously, we would say that no, the black body is traveling very fast in vacuum, and it's leaving behind this ooze of black body radiation. And so it's losing mass. The black body is losing mass, and that mass is appearing in the energy of the black body radiation. And the luminocentric principle is saying that the energy it left behind is stationary, that it's the black body that moved. So I hope this helps. Thanks for watching.